So what is infrared? This is a image of the electromagnetic spectrum. It's around you all the time. That goes from a wavelength of 0.01 nanometers. A nanometer is a billionth of a meter, up to about 30,000 meters. And that covers everything from gamma rays, cosmic rays, ultraviolet rays, visible rays, infrared, and different radio waves. Out of all of that cycles of energy, the only thing the human eye can see is about 400 to 700 nanometers, a very small part. Everything else is invisible. Most sunlight is invisible to the human eye. So what we're going to do is compress this down and talk about exactly what infrared is versus the other things. Now the rainbow you see in the image is the visible light. That's the bands of light broken through a prism that shows all the colors that we can see. Infrared is a longer wavelength than visible, and it cannot be seen by the human eye. Sir William Herschel in 1800 was observing the sun through different colored filters, and he noticed that some of the filters, the image he was seeing or feeling was hotter than some of the other colors. So he decided he was going to try to figure out why that was. So he put up curtains, very dark curtains over his windows in his lab, and left a very narrow band open and let the sunlight come through. And he ran it through a prism, and he split the spectrum of all the different wavelengths of light with the colors. And violet was the coolest, all the way up through red, which is the warmest. But he noticed as he moved the thermometer beyond red, the temperature actually went up. So he named that area, an invisible area, infrared, or beyond red. The energy is transmitted three ways. There's conduction, which is direct contact. There is convection, which is like you're heating a room with heat flowing from a furnace or air conditioning, and it movement of molecules against other molecules, and soon you will reach an equilibrium. The most powerful method of energy conduction is radiation, and that's what we're concerned about. Radiation will work in a vacuum. It works at the speed of light, and it works through all the other mediums that you use. And so we're going to be concerned with that with our infrared instruments. Anything above absolute zero, which is 0 Kelvin, minus 273 C, or 459 Fahrenheit, transmits energy or emits energy. Scientists tell us that absolute zero is the point that all motion stops, or at least that all transmission of energy from one point to another stops. Infrared thermometers are passive devices. They don't do anything to get the readings that they get. A lot of people think on the small infrared thermometers with laser sights, when you pull the trigger and the laser dot appears on the target, that bounces back and the instrument is reading that. It does not. Infrared thermometers use a parabolic mirror to gather light or gather energy, and concentrate it on a thermopile, which is a cluster of specialized thermocouples, and that gives a temperature reading through electronic conversion in the instrument. This is an overview of infrared energy. You have to the left short wavelength, in the middle there medium wavelength, and then long wavelength. You'll see some areas that are blank in there, nothing is showing. That means that water vapor in the atmosphere or gases in the atmosphere have blocked all transmission of that wavelength, so there's nothing to measure. You'll also see that there is not 100% transmission anywhere on the scale for infrared energy. Infrared only measures surface. There's a lot of movies and TV programs you'll see where Hollywood demonstrates that they can see through walls and see buildings or people inside of buildings. It's not so. Nothing is measured except the external wall, and at the long wavelengths that these things are taking place, and the energy will not go through the glass of the windows. This is an example of infrared seeing through something other than on the surface. The long wavelength infrared will go through thin plastic, so you can see where you can see the people inside the garbage bags. There are specialized spectral ranges that will read the plastic surface only. Infrared temperature measurement is an inexact science. There's nothing touching the surface of the target we're measuring, so there's issues to think about. Very high accuracy thermometers, infrared thermometers, under ideal conditions can be accurate to as much as a 0.5 degree C or 1 degree Fahrenheit. But that means the electronics, all electronic products are affected by ambient temperatures around them. They operate, say, at 75 degrees, plus or minus 10 degrees at the best. And as you go above or below that, the performance begins to suffer slightly. Over time, it will build up. So in a very hot environment, the infrared instrument is not going to give you this kind of accuracy. So it has to do with the issues that are around it that affects its ultimate accuracy. But most of the real accuracy you get in the field on a very high instrument, high accuracy instrument, might be 0.2 of a degree or 2 degrees C or 2% of reading, whichever is greater. The real thing that people are interested in with an infrared thermometer is setting it up and getting a good product and then having that instrument repeat over and over the same points so that they get consistent, good quality product. So it's important that when you're setting it up that you reach those things that get what you want, that you set it up to get the readings you want and have an instrument that will maintain that accuracy. So we're going to go through some pictures here of issues where you might want to use an infrared thermometer instead of a contact thermometer. And those have to do with very high temperatures, all the way up to 3,000 C, which would be very dangerous for an operator to be close to. Dangerous areas where an operator has to walk in around among things that are dangerous for him to be in order to get a direct line of being able to touch his target. Moving objects, things can be moving at different speeds. It's difficult sometimes to get a reading on something with a contact thermometer when it's moving away from you constantly. Also delicate objects that might be damaged or broken by touching them with a contact probe while they're moving, or a surface temperature on a very small object. The probe will actually pull heat out of that surface and you will get a wrong reading until you allow it to restabilize. Continuous process where you're trying to monitor something going on and you want to control it or record the temperatures. It's difficult to do if it's a dangerous process. Objects with low mass, those things are difficult to read with a contact thermometer because you're pulling heat out, and thin film sheets of plastic, you can't do it without breaking them or creating a hole in them. Object with rough surfaces. With a contact probe, you have to have a flat surface. Can't be rounded or have dimples in it because you have air gaps around the probe contact point. And then objects at a distance, it's difficult to read something at a far distance. You can do it with an infrared thermometer, but getting to that maybe, if it's up on a pole or up on a scaffolding, it's hard to get to. So you can do it with an infrared. And then durability. Contact thermometers will get broken or will fail. Very high temperature contact thermometers, you get a temperature dip into molten steel maybe 1 or 2 times before the probe tip is destroyed. This is a handheld, or with a new handheld DHS-40 series of thermometers. These have the same spectral ranges and attributes of our fixed mounts, so you can use these to monitor and help set up a fixed mount or monitor things on a periodic basis. As you walk around, the quality control people can use them.